Geology lesson number 12. All right, so lesson number 12, geology lesson number 12. And today we're going to talk about how to find the epicenter of an earthquake. So if you remember, the epicenter is the location directly above the hypofocus. So think of the earthquake, and we have these plates. Okay, so we have, this could be a Pacific plate, North American plate, this one's going south, this one's going north, and they get tangled up, they get trapped. That area of entrapment, when there's a lot of pressure building up, it's called the hypofocus, or the focus of the earthquake. And it's usually, well, it's below the surface of the earth. Right above that, though, is called the epicenter. So the epicenter is directly above the hypofocus. So it's on the surface of the earth. And we want to find out where earthquakes originate from. Generally, we're talking about epicenter, even though scientifically they originate from the focus. Okay, so how do we find the epicenter? Now, if we go back to waves, let's go back to thinking about the waves of the earthquake. So we have seismic waves, are waves produced from an earthquake. The three types of waves. We have number one are called P waves, and those are the fastest waves. They travel in the direction, the waves travel in the direction the matter travels, and they can go through liquids and solids. The next one, those are actually the primary waves, they're longitudinal waves. Second type of wave are called the S waves. The S waves, think of a slithering snake on a solid sidewalk. So they go sideways, or they're called transverse, across, and they can only go through solids. So they move like a snake, and they're a little slower than P waves. And then we have surface waves, which are the waves we feel on the surface of the earth. Now, P waves travel a little faster than S waves. So we can tell how close we are to the earthquake, the epicenter, by the difference between the arrival of the P wave and the S wave. So in a seismometer, which detects these waves, and when it detects the P wave first, obviously, and then this S wave comes next, if it's a short amount of time between those two, that's called the lag time. If that's short, the earthquake is relatively close. So the longer the lag time, the longer the distance between the arrival, the difference between the arrival of the P wave and the S wave, further away you are from the earthquake. But how do we know? Okay, so we don't know where it is. So let's say right now we are in this is a seismometer station right here. So Brutus is going to be the seismologist, his manager. So you're telling Brutus, all right, we've got a P wave came in at 7 o'clock this morning, and 7:05 we have an S wave come in. So we're 5-minute lag time. Okay, so let's say we've been determined now to be 100 kilometers from the earthquake, right here, at the earthquake epicenter. But we don't know if it's 100 kilometers that way, 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 that way. We don't know. Woo! I can't do that anymore. Hold on, getting dizzy, vertigo. Okay, so we don't know the direction. So this is what we're going to try to figure out today. And what seismologists use, seismologists study earthquakes, we can see this, is called the triangulation method. So, how am I right to determine location of epicenter. How do we determine where it is? Okay, so I'm just going to draw and we're going to say we're here in the United States. I'm going to say this is Burlingame right here. All right? That's where we are. Well, I'm in San Jose. We're going to talk Burlingame. Okay. Then we have Miami. And then we have New York. Okay, so these are 3 seismology or seismometer stations. This is where we can, they're all over the world, right, to determine these earthquakes. But I'm just giving you examples, 3 different stations. All right, so we have one in Burlingame, one in Miami, and one in New York. Let's just say they're spread out, so 3 of them. Okay. I can figure out, so we're in Burlingame. I've determined, let's say, this earthquake, let's say we already determined it was 200 kilometers away, but we don't know what direction. It could be 200 from this way, this way, this way, this way. We don't know, but we know it's 200 kilometers from this, okay? Because this is where the seismologist is. This is where you and Brutus are studying these earthquake waves that just came in. And you determined that, so we don't know where it is. So we're going to draw a circle to end. It could be anywhere on this circle. Okay? In New York, let's say their station, they determined it was 3,000 kilometers away. So 3,000. So I'm going to go, okay, now this is just, obviously, this is not to scale, by the way, I'm just demonstrating how this process works. This is triangulation. So, 300 kilometers. So that means that could be, 3,000 kilometers from that center. So anywhere along this circle. Now, if we only have these 2 readings, or seismology stations, seismograph stations, we could say the earthquake epicenter could be here where they intersect, or it could be here, but we don't know. So that's why we need a 3rd station. Okay, so let's say Miami now. The waves came in, and they were determined to be 2,000 kilometers away. Same thing, it could be any direction, so we're going to draw a circle. And let's just say, this is obviously not to scale, okay? Just want to make sure I'm not doing it to scale, I just want to show how this is done. So that station received the waves. They were able to determine the epicenter is 2,000 kilometers away. They don't know what direction, so it could be anywhere on the circle. But if we put all of them together now, where do they all intersect is right here. So this, not this one, because we have 3 now. So right here, this is the epicenter of the earthquake. So this is how geologists, or specifically seismologists that study earthquakes, this is how they determine the epicenter, the location of the epicenter of the earthquake. Okay, so this process is called the triangulation method, because tri means 3. We're using information from 3 seismic stations, or places that measure these earthquake waves. So triangulation means finding the location of the epicenter of the earthquake using the location of other things. So in other words, using the location of other seismic stations. All right, so it's a way that scientists can determine where this epicenter, where the earthquake started. All right, and they use that based on those S and P waves coming in, and also the location of other seismic stations. So that is what triangulation is. The steps, okay, so if I just went over how to figure out the epicenter, but I want to put them into steps. The first step would be to figure out the distance they are from the earthquake. So distance. The number this number 1. So this is in Burlingame. Let's say this 2 is in New York and 3 is in Miami. Okay, 1, 2, 3. Okay. So first thing I would have to do in triangulation, step number 1, is to determine the distance they are to the earthquake. So how far is number 1 to the earthquake? How far is number 2 to the earthquake? How far is 3? And we did that. So we said this one was 200, this one was 3,000, that was 2,000. All right, and we didn't know the exact direction, so that's why we drew circles around them. So that's step 1. The next step is to obviously draw like a circle around each of these, because this shows where this earthquake epicenter could be located. And then that's step number 2. So I'm going to draw a circle around them, indicating that distance. So the radius of the circle would be the distance from the earthquake. Okay. And the third step then is to look at where they intersect. So the third step, this is the place where all those circles came to get intersected, so that is the epicenter. So the 3 steps, number 1, you figure out the distance that each of these seismometers are located from the earthquake. So how far away? Step is to draw a circle around each one, indicating that distance. And then number 3 is to figure out where they intersect. And that's your epicenter of the earthquake. So we went over the 3 steps of the triangulation method to find out where the epicenter of an earthquake is. Step number 1 was to find the distance to the earthquake from each of these seismometers or seismic stations. Right? Step 2 was to draw a circle around each one, indicating that distance. And then step 3 is to locate where they intersect, and that is your epicenter. So if I go back to the first step, how do we find the distance though? So how do we find this distance we are from an earthquake? So the difference between them is an indication of how far the earthquake is. The larger the distance between the S waves coming in and the P waves, the further away the earthquake is. So if the P waves come in and the S waves right afterwards, you're close to the earthquake. If the P waves come in and it takes a long time, the S waves finally come in, you're further away. And we can determine the exact location using a timetable graph. And I'm going to show you right now how to get that number. In other words, how to get the distance you are from the earthquake, because that was part of step 1. This is called an earthquake P wave and S wave travel time graph. And what this shows is really the speed of the S and P waves. On the x-axis we have the epicenter, the distance, and this is in kilometers, and we have to multiply times 10 to the 3rd kilometer, so each one of these is actually, you should add 3 more zeros, so this is 1,000, 2,000, 3,000, 4,000, so forth. On the y-axis, we have the travel time, and this is the time it takes for these S waves and P waves to travel. We can use this to determine the distance we are from an earthquake. So if we have a seismometer, we can determine how far away we are from the actual earthquake if we have the S and P waves recorded. So each one of these is actually, you should add 3 more zeros. So this is 1,000, 2,000, 3,000, 4,000, so forth. On the y-axis, we have the travel time. So we take that lag time, and our lag time for the example was 10 minutes. So I'm looking on the x-axis. All right, these are in minutes. So here's 10 minutes. What I'm going to do then is draw a line up to 10. And then I'm going to find a place between the S and P where this line will actually fit. So, looks like right there. So, this lag time fits perfectly right here. And that indicates, that lines up right here with 9. So the epicenter is 9,000 kilometers away if you have a lag time of 10 minutes. So we can use this information now to determine the distance we are from the epicenter of the earthquake. Gotta be a better way to do this. There's I'm going to take a sheet of paper and I'm going to put it in the corner of the graph, line it up with the 0, so 0 is right in the corner. Okay, and I want to mark up to 10. So I'm going to draw a line. I put it in a corner because this is 10 is our lag time. Okay, draw 2 lines, you can do that. But I just took the corner, lined it up to 10. Now the distance here is my lag time. Distance between here to here. And I want to find where that would fit on the graph here. Look, so this is where they fit. And we go down, and it's 9. It's going to be the distance to the epicenter. Now I want to know, when did this earthquake actually happen? So we have a lag time of 10 minutes. We have the distance 9,000 kilometers. Geology rocks. You rock. Rock on, rock stars.